Hello. Today's lecture is about design for manufacturing, DFM. The core idea of DFM evolved in response to what is called traditional sequential engineering, where designers used to design the product and throw it over the wall to manufacturing, and then let manufacturing figure out a way to make the product. This required many expensive iterations between design and manufacturing before a final agreement was reached on product features that are manufacturable. More recently, concurrent engineering practices started being popular. The key concept behind the concurrent engineering philosophy is to incorporate downstream concerns during the early phases of design and development. So, incorporating manufacturing concerns in design and development is referred to as DFM, Design for Manufacturing, and considered to be one of the core CE practices, concurrent engineering practices. Some of these DFM ideas, tools, and principles, which I will describe today, may also be customized for other DF, Design for areas that has been historically underrepresented in design, such as assembly, then we call it Design for Assembly, DFA, or environment, then we call it Design for Environment, DFE, or reliability or safety, or so many other concerns. There are lots of approaches to DFM. The approach that the book adopts is a cost-based approach. That is, DFM is ultimately about cost reduction without sacrificing quality. I will talk about where DFM fits within the overall picture of the product development process. Then I will describe the DFM method. These are the usual 6 phases of the product development process. The question is, how can we emphasize manufacturing issues throughout the development process? DFM does not fit neatly into any one of these stages. It is often applied in the detailed design phase, where we already have the concept and we are figuring out the details of the design. Here we start thinking about tooling and production methods. However, even during concept development, it is helpful to think about the production techniques that are available, by what methods we will produce and assemble the components. This can actually affect our concept generation and selection. That's not exactly DFM, but it is an impact of DFM thinking and philosophy at the early stages of development. We may even go as far as the planning phase, where an understanding of manufacturing capabilities and constraints will have an effect on what projects to pursue or concepts to pursue. This example, you will read about it in your book about the GM 3.8 liter V6 engine. It is a good example because it illustrates the cost estimation in a detailed way and was explained well in the book chapter. We will not talk much about it today in class, but we will use our own example instead. Here is a formal definition of DFM, Design for Manufacturing. DFM is a development practice emphasizing manufacturing issues throughout the product development process. The key words are emphasizing manufacturing throughout. It's easy to emphasize them later on when we are in the production ramp-up phase, when you are starting to build the tooling and so forth. But to emphasize them early requires some special attention and tricks, which we will look at today. The result of successful DFM, Design for Manufacturing practices, is lower production cost. Since we will look at DFM from a cost perspective, let us take a closer look at what constitutes manufacturing cost. There are the cost of components, there are the cost of putting these components together, assembly cost, and there is the overhead cost. 2 types of components, standard components and custom components. Standard components are off-the-shelf items like motors, switches, and screws. Custom components, on the other hand, are made to order from raw material according to the manufacturer's design specs, either in-house or possibly at a supplier. They are raw material, processing the material, and then tooling costs. Assembly is about 5 to 10% of the total cost, manufacturing cost. But even so, if we focus on how we put the parts together, the savings are not merely due to reducing assembly time by streamlining the assembly process, but also by forcing us to think about reducing the number of parts. The biggest impact of DFM is to do part integration and reduction or reduce the number of parts. Overhead costs are all other costs not included in components or assembly. These are usually divided into two categories: support costs and indirect allocations. Support costs are costs of support systems required to manufacture the product, but usually shared with other product lines, such as material handling cost, purchasing cost, shipping, and receiving. Indirect allocations, on the other hand, are costs that cannot be directly linked to making a product, such as the cost of, say, heating the building or salary for the security guards, something like that. Another way to divide manufacturing costs is between fixed and variable costs. Fixed costs are the costs incurred regardless of the number of units produced, such as machinery and tooling. Variable costs, on the other hand, are costs incurred in proportion to the number of units produced, such as raw material costs. As I said earlier, there are many methods that a company uses to implement DFM. Here are three of them that are commonly used in practice. The chapter does not address these explicitly, but mainly one of them, the cost-based approach. The first is an organizational method and called cross-functional teams to get design engineers and manufacturing engineering together early on. Just by getting the people working together closely, you can improve manufacturability. The manufacturing engineer would have a chance to comment on the design in advance and give early input to product designers. The second approach is the design rules. A list of design rules or guidelines for improving the design, which will be followed by product designers. That's what is called design rules. So basically, engineers would be carrying maybe in their pockets, those plastic cards that have a list of rules that they should follow when designing their products. And these can be really they can be company specific. Let me show you a list of design rules that are used for a computer manufacturer. These rules were printed out on plastic cards in engineers' pockets. The idea is if you simply follow these guidelines, our products will be better and easier to produce. So let me read these rules and talk about some of them a little. Remember that these are particular to a computer assembler or computer manufacturer. Some may be generalizable. One of particular interest we will use frequently is the stack assembly. Anyone would figure out what stack assembly. Stack assemblies, sometimes called Z-stack assemblies, which mean that if we can assemble things in the Z direction, basically XY being the horizontal plane and the Z being the vertical plane, or the vertical axis, then gravity will actually help us. It helps us to stabilize the parts, so you don't need to have tooling and fixturing to hold the things together while you go to other things. While if you do things from the side, or try to plug things from the side, gravity works against you and may misalign the parts that you were trying to insert or assemble, and you may need tooling and fixtures to hold the things in place or the parts in place while you do more assembly. So in general, if you start from the bottom and then build up and then put the top on, a lot of products are assembled that way. This is called Z-stack assembly. Here are the generic steps followed in most DFM practices. It starts with choosing a candidate design and performing the following on it. Estimate manufacturing cost of parts, reduce the costs of making the components, reduce the cost of putting the components together, that is assembly, reduce other supporting costs if possible, modify the design, and repeat the process. Of course, we choose the design with the lower overall cost. Cost estimation. Let us start with estimating the cost of components. Standard parts usually are estimated by soliciting price quotes from suppliers. When soliciting quotes, estimated production quantities are extremely important for price breaks. Note that some suppliers will design and facilitate and fabricate a custom variation of a standard part if production quantities warrant that are high enough. Vendors of standard parts can be found usually in the Thomas Registry of American Manufacturers. Custom parts. It's composed of raw material, processing, and tooling. Raw material can be estimated from the mass of the part, allowing for some scrap, obviously, and then multiplying by the cost of material per unit mass. And the cost of material can be found in Appendix A in the textbook, like an Ippinger textbook. And I'll take a look at one of these tables in the next slide. But processing cost includes the cost of operator and cost of operating the machine. Anywhere between $25 for simple stamping press to $75 for CNC milling machines. Various part manufacturing costs for stamping, casting, injection molding, and machine parts are shown in Appendix B of the chapter at the end of the book chapter, which may help you in your project actually. I will also look at one of those tables in the next few slides. Then the tooling cost, which can be estimated as follows. Tooling costs such as molds, dies, and fixtures. The unit tooling cost is simply the cost of tooling divided by the number of units to be made over the lifetime of the tool. Appendix B in the book chapter, at the end of the book chapter, also have some approximate tooling costs for a variety of shapes and parts. Moving on to the assembly cost, how do we estimate that? For products made in quantities of less than several 100,000 units a year, assembly is almost always performed manually. Some exceptions are for PCB assembly, for example. For these, assembly costs can be estimated by summing all assembly times and multiplying by the labor rate. Assembly operations require from about 4 seconds to 60 seconds depending on product size and insertion difficulties, among other things. Appendix C at the end of the chapter also contains a table of approximate times for manual assembly of various products, which may also be useful and handy to use for your project. Overhead costs. Most firms most firms assign overhead costs by using overhead rates. Overhead rates are typically applied to one or two cost drivers. Cost drivers are parameters of the product that are directly measurable. Common cost drivers are cost of any purchased materials, cost of assembly, labor, and the number of hours of equipment time the product consumes. Overhead charges are added to direct costs in proportion to the drivers. Example, let's say the overhead rate for purchased material is 10%, or overhead rate for assembly labor is 80%, then a product consisting of $100 of purchased components and $10 of assembly labor incurs $18 of overhead costs. That is 10% of the $100 plus 80% of the $10. That comes up to $18. As I told you, I will show you one of the tables. This is an Appendix A at the end of the book chapter. And it shows the average or the range of costs for common engineering materials. Ranges for different grades here, I believe. So they range, for example, you pick a specific material and this is the range of the cost. And I think that range is due to different grades for the same material. As I told you, this may be helpful for your project based on the various materials that are listed here and their associated costs. This appendix also in your book at the end of the book chapter, and the appendix at the end of the book chapter shows examples of components and their cost data for CNC machining, for injection molding, for progressive die stamping, sand casting. This particular slide shows an example for CNC machining cost example. This one is also taken from the appendix and at the end of the big chapter, and it shows assembly data for common products. Again, you would look at what is particularly close to the situation that you're dealing with in your project, and then you can estimate, in this case, the assembly cost. The second step of the DFM process is to reduce the costs of making the components. Steps to keep in mind when trying to reduce part manufacturing costs are: 1. Understand process constraints. A designer may specify excessive tight tolerances without appreciating the difficulty or cost of achieving such accuracy, or without regard to the manufacturing capability of the firm. Designers need to be aware of what type of operations are difficult or unavailable and try to avoid them. Second point is eliminate process steps by using net shape fabrication processes if possible. Net shape processes are those that produce a part with the final intended geometry or close to it in a single manufacturing step. Typical examples are molding, casting, forging, and extrusion processes. Create a part close to final requirement and may demand only minor additional processing, such as drilling a hole or cutting to length. The third thing is economies of scale. Leveraging economies of scale. A, fixed costs are divided among more units, and B, variable costs become lower since the firm can justify the use of larger and more efficient dedicated processes and equipment. But in order to leverage economies of scale, we need to standardize the use of parts and processes. Use the same parts across multiple product lines if possible to increase production volumes or to increase production volumes. Black box designs allow suppliers to design and manufacturing parts by only providing suppliers with part specifications and not the details of how to design and make the part, thus giving suppliers a lot of flexibility and freedom to develop best and more economic methods of production. The third step is to reduce the cost of assembly. The most popular DFMA, design for manufacturing and assembly software, is made by Boothroyd and Dewhurst. The method is developed about 20 years ago. Now they have 80% of the market share. The method estimates the time it takes to assemble parts together based on their geometry. The basic idea for design for assembly is that we are minimizing the parts and maximize the ease they go together. They specifically focus on the handling and insertion. They specifically focus on the handling and insertion in their DFA software. But how the parts are made is another module. So we're going to talk about only in this slide about handling and insertion. Benefits of this: if I'm going to make assembly easier, which means faster, then the lower the labor costs of assembly, that is the direct benefit. How about the indirect benefit? Yes, there is. Less faulty assemblies due to decrease of probability of error. Any others? Probably fewer parts means fewer parts to track in my inventory, so less complicated supply chain inventory management system. It also means faster response to customers when you have fewer parts. Automated assemblies are easier. The bottom line is lower direct labor costs are not the only benefit for design for assembly. There exists other indirect benefits. The idea behind the software is this: we want to minimize assembly time. So we want to make assembly time clear and visible. So this is what it takes: handling time and insertion time. Then you can relate assembly time to assembly cost by multiplying by labor rate, as I said earlier. Handling time is the time it takes to handle and manipulate the part to get it in place. Insertion time is once you get the part in place, what you can do with it. Do you just drop it, or do you have to hold it down and screw it or whatever? So the idea is engineers have a candidate design and they do this computation and it calculates an assembly cost. Then they do a redesign and compute the assembly cost again and take the cheaper one. It is not a whole lot deeper than that. The software works by asking designers a series of questions about their design to estimate assembly time, such as, can you do it with one hand? Or do you need two hands for manipulation? Or do you need two hands because the part is very large? Say you answered one hand with a grasping aid, then it asks more questions. Do the parts need tweezers or other tools for grasping and manipulation? Can the parts be manipulated without special magnification? How much orientation you have to do, and so on. Based on all these answers, the software provides an assembly time estimate. The last step in the DFA method is to reduce the number of parts by integrating parts together. So how do you reduce the number of parts? According to Boothroyd and Dewhurst, you need to answer 3 questions. If the answer is no to all 3, then you probably can combine these parts together. The first question is, does the part need to move relative to the rest of the device? Is there relative motion? If not, maybe I can combine the parts together. Does it need to be of different material because of fundamental physical properties? Otherwise, maybe I can combine them together. Third thing is, does it need to be separated from the rest of the device to allow for assembly, access, or repair? Again, if not, maybe you can combine the parts together. If you are clever, you can figure out a way of combining them and then see if that is cheaper, faster, better to make the combined part. This actually going to be the basis of any part integration method. Okay, so you are going to think about this: can I integrate parts and reduce the count of a product?